Okay, the last part of section 9.2, tests for proportions, I think is pretty intuitive, I hope, at least at the level that we're going to go into it. It's about why confidence intervals might sometimes give more information than the hypothesis test itself. So this is going to be a continuation of the example from the previous video about Taeyeon wondering if the smoking, or the non-smoking proportion at his school is different from the national average of 0.5. So in that example, we did a two-tailed or two-sided hypothesis test, and we had pretty strong evidence that it was something different than 0.5. We rejected the null hypothesis of it being 0.5, which means we had evidence that it was something other than 0.5, but really, beyond that, that's all we really had. Now, confidence intervals tell us a little bit more sometimes. So here's a quick reminder, right? Taeyeon asked 150 kids, 90 of them said, hey, I've never smoked, checking the conditions and doing all the things for a confidence interval. Remember, his p hat plus or minus z star times square root of p hat times 1 minus p hat all over n would give this confidence interval. Of course, that's a one prop z interval on your calculator. This says we are 95% confident that the true proportion of kids at his school that have never smoked is between 0.522 and 0.678, between 52% and about 68%. If I'm 95% confident it's between 52 and 68%, what do you think about the chances that it is 50%? I think it's pretty obvious, at least at the surface level, if I'm 95% confident that it's between here and here, that gives me pretty strong evidence to reject the idea that it's 0.5. It's not even in this interval. Am I 100% certain that it's not 0.5? No, but I'm pretty darn sure. This confidence interval not only tells me I should probably reject a hypothesis that p equals 0.5, I also have pretty strong evidence that it's higher than 0.5. It's something between 52 and 68%. So this confidence interval gives me more information. Here's the same confidence interval. This is if it was kicked out from your computer instead of you doing the calculations. This between 52 and 68%. Same thing. It tells it in one place. Here's the confidence interval. That's a test statistic of 2.45, which would have a p-value of 0.014. That p is low. I would have rejected my null hypothesis that it's 0.5. But that's kind of built right in here, right? So it kind of gives both pieces of information, but the confidence interval gives you some information about if you would or would not have rejected the null hypothesis. Now, if you are interested, there's some kind of cool stuff about why that works. And it all makes sense. It's all legit. It's not 100% sure because statistics means never you're having to say you're certain. But this picture and this page goes through the why is that true. But for our purposes, I want you to know this. If the confidence interval doesn't contain the stated proportion from the null hypothesis, that's pretty strong evidence to reject that null hypothesis. If that null hypothesis happened to be in the confidence interval, then we would say, oh, we would fail to reject because I think there's a chance that that proportion is in my interval. If it's not in there, reject. If it's in there, fail to reject. That's the big takeaway. And that's the advantage of confidence intervals over hypothesis tests. So that's it for 9.2.